In this series of lectures on thermodynamics of electrochemical cells, in lecture 4, I shall try to develop the Nernst equation of this cell potential. And this one is the very important equation in electrochemistry. And then again I shall try to explain how the potential in a reversible electrode is being developed and how it could be determined by means of an experiment. Let us take this cell reaction. This cell reaction, nu1A1 plus nu2A2, and giving you this nu3A3 plus nu4A4. A1, A2 are the reactants and A3, A4 are the products, and nu1, nu2, nu3, nu4, these are the stoichiometric coefficients of these cell reactions. We can write this one 0 equal to minus nu1A1 minus nu2A2 and plus nu3A3 and plus nu4A4, or in short it can be written as summation of nu I and AI, where nu I is negative for reactants and positive for the product. As the reaction proceeds spontaneously in the forward direction, the free energy of these cell reactions is beginning to decrease. This cell reaction begins to decrease, and this decrease in free energy is converted into the electrical energy by means of a device which we call the galvanic cell. And this free energy change for this reaction equal to this summation minus nu1 m1 mu1 minus nu1 mu1 minus nu2 mu2 and plus nu3 mu3 and plus nu4 mu4. This mu1, mu2, mu3, mu4, these are the chemical potentials of these reacting components A1, A2, A3, A4. These chemical potentials is a very important term in thermodynamics, and chemical potential actually means the partial molar free energy. Its importance in chemistry is very high, and this is why it is gives a new name which is called the chemical potential. And this one you can write this summation of mu I and mu I. This mu I, summation of mu I and mu I actually depends on this activity of this ith component, and so this is equal to mu I naught plus RT and ln AI. This AI, the activity of this ith component, and mu I naught is the standard chemical potential of this ith component. It is the chemical potential of this ith component when its activity is equal to 0. So this one we can write a summation of nu I and mu I naught plus RT at a constant temperature, and it is summation of nu I and ln I. Or this one actually gives the free energy, standard free energy change of this reaction, and this is equal to del G naught and plus RT and ln and this capital point, which is the notation for this product, and AI and to the power nu I. This free energy change is a very important property of this cell reactions. When it is negative, this cell reaction occurs spontaneously in the forward reactions. When it is zero, this cell reaction at equilibrium. This del G, whenever it is negative, then this back reaction is spontaneous. Delta G naught is a characteristic property of these cell reactions at a given temperature, and this one actually capital phi and AI nu I equal to A1 minus mu 1 into A2 minus mu 2 and A3 mu 3 and A4 to the power mu 4, and it could be written as A3 to the power mu 3 into A4 to the power mu 4 and divided by A1 to the power mu 1 and A2 to the power mu 2, and this one written in short is QA and called the activity quotient. This activity quotient is the ratio of the activities of the products, and the coefficient will go to this power and divide upon the activity of this reactants. Again, the power coefficient will go to the power of each activity. These activities are arbitrarily chosen activity of these reacting components in a cell reactions. Arbitrarily chosen means the activity of these reactants and products have been taken according to our own choice in this cell. So this one del G equal to del G naught and plus RT ln, we can write QA activity coefficient, and this is the Hoff equation. This is called Hoff equation. And another equation I can also write this Hoff equation. Whenever free energy, whenever the reaction occurs spontaneously, the free energy is decreasing, and whenever the free energy attains this minimum value, then delta G equal to 0 and this reaction attains equilibrium. In this case, this QA is equal to the activity equilibrium constant, as these activities at that time becomes the equilibrium activities of these reactions. So del G not equal to, so at equilibrium, when this reaction attains equilibrium, this delta G equal to 0 and delta G naught plus RT ln Ka, or we can write del G naught equal to minus RT ln Ka. This one and this one are called the Hoff reaction, isotherm of this cell reaction. So whenever we transfer this Hoff equations to this Nernst equation, we have to jump from this thermodynamics to electrochemistry. So in that case, this del G equal to, in this case, this del G instead of del G, we can write minus NF E shell. We are coming from this thermodynamics to this electrochemistry to build up this Nernst equation, and this one equal to minus NF and E cell naught and plus RT ln QA. This one is the standard cell potential. It means it is the potential, it is the cell potential when the reacting, each of this reacting component activity of each of the reacting component is taken 1. So dividing by NF, it becomes E cell equal to E cell naught minus RT by NF into ln QA. And this equation, again this equation, del G naught equal to minus NF E naught cell, and this one also equal to minus RT and ln KA. So equating this one, we get this E cell naught equal to RT by NF into ln KA. This form is very often occurs in this Nernst equations. These two are the Nernst equations. So it is our practice to express this term with a numerical value at 25 degrees centigrade. At 25 degrees centigrade, which is a very common temperature, this RT by F, and this one we can also write, E cell equal to E cell naught minus 2.303 N RT divided by NF and log QA. And this one, so at 25 degrees centigrade, 2.303 RT by F equal to 2.303 into the value of R in joule, 8.31 joule, mole inverse, Kelvin inverse, and 25 degrees centigrade means temperature 298 Kelvin, and divided by the Faraday is 96,500 kilomole inverse. So mole inverse cancels, Kelvin cancels, and this will give you this 0.059 and joule by coulomb, it is the volt. So these cell reactions, this Nernst equation would be written as E cell equal to E cell naught minus 0.059 by N and log QA. QA is the activity quotient of this cell reaction, and E cell naught equal to 0.059 by N and log Ka. This equation. These two are the Nernst equations at 25 degrees centigrade, and these equations are widely used to calculate the cell potential at a given activity quotient of this cell reactions. And this relation is also used widely to calculate the activity equilibrium constant of this cell reactions. Now I I shall try. Here I can write this equations. E cell equal to E cell naught minus 0.059 by n and log QA. These are the Nernst equations, and E cell naught equal to 0.059 by n and log KA, and this is QA. These two we can call the band of these two we call the Nernst equation. Nernst equation used to calculate Nernst equations of this electrochemistry used to calculate the cell potential of this galvanic cell. Now I shall try to explain how the potential is developed in a reversible cell. How the potential is developed in a reversible electrode, and how this electrode potential could be determined. For this purpose, let us write the more popular, the Daniell cell. This is the Daniell cell, and here the zinc sulfate solutions, and here the copper sulfate solution, here the porous barrier, and here the copper electrode is deep, and here the zinc rod is partially dipped. So this is the element, and this one is the porous barrier. This porous barrier actually prevents the premixing of the zinc sulfate and copper sulfate solutions. These two are the terminals. These two are the terminals of this Daniell cell. This is Daniell cell. Daniell cell. Very popular, and its representation we know this zinc sulfate solution and salt bridge or porous barrier, and copper sulfate solutions and pure copper. This is the positive electrode, and this is the negative electrode. We know the copper. Now I shall try to explain how the potential is developed in each of these electrodes. And zinc is more electropositive than copper. So in this case, zinc will be oxidized to zinc ion, and copper ion will be reduced to copper atom. And here some zinc ion is coming up or dissolved from this zinc plate, and here some copper ion will be deposited on this plate. So in this case, these reactions, electrode reactions, we can write this Zn plus 2 plus twice E, and it is oxidation. And in this case, we shall write copper plus 2 plus 2E, and giving this copper, and it is the reduction. So whenever a minute amount of zinc is dissolved in this solutions forming this zinc ion, this solution becomes positively charged due to excess of this zinc ion. And this further dissolution of this zinc ion will, these solutions will prevent. And whenever zinc is dissolved in zinc atom is dissolved in as a zinc ion, 2 electrons are being left, and these 2 electrons are left on this zinc metal plate, and so this one is the negative charge and called anode. Whenever a small amount of zinc is converted into zinc ion, this reaction stops due to positively charged of these solutions will prevent the further dissolutions and equilibrium will be established. And whenever equilibrium is established at this phase boundary, solid and liquid, we are having this charge separation. This is the negatively charged and this solution is positively charged, and this charge separation and this phase boundary will produce the potential difference, and this potential difference we call the electrode potential, and this electrode potential can be written as E zinc to zinc plus 2. It is the oxidation electrode potential of this electrode. Here also similar phenomena will occur whenever the copper is less positive than zinc. So copper ion will be deposited here as copper atom, and 2 electrons this copper ion will take up from this copper metal plate. So whenever 2 electrons will be taken up by this copper ion from this copper plate, it becomes positively charged. So this one is positively charged and it is called cathode. So further deposition of zinc ion will be prevented by the negatively charged of this copper sulfate solutions, as whenever the copper ion is deposited, there occurs an excess of the sulfate ions and the solution becomes negatively charged, and the further deposition will be prevented. So here also this equilibrium will be established within a short time. So whenever the equilibrium attains, this one is positively charged, this one is negatively charged, again there occurs a charge separation, and charge separation will produce the potential difference, and this potential difference we call the electrode potential of this electrode, and it is written as E zinc copper plus 2 to copper. It is the reduction potential, it is the oxidation potential. These are all the reversible electrodes. The cell is reversible and the electrodes also, the cell also constitute the reversible cells. In case of reversible cells, the reactant and product of each electrode will remain in equilibrium, will be present in contact with each other. Here also copper and copper ion, they are also remaining in contact, and so this is also reversible electrode, this is also reversible electrode. But if this zinc rod is dipped in a sodium chloride solutions, then it will not be the reversible electrodes. So this is the oxidation in the left hand side, this is the reduction in the right hand side electrodes. If we add these two electrode reactions, then it becomes zinc plus copper plus 2 solution. Zinc is metal solid, and giving this zinc plus 2 solution and plus copper solid. This is the cell reaction. And as the summation of these two electrodes gives the cell reaction, so naturally the summation of these two electrode potentials will also give this cell potential. So cell potential will also be the summation of these two electrode potentials. We can write Cu plus 2 oblique copper. This is the reduction electrode potential, and plus this one, this zinc to zinc chloride, zinc plus 2, and this is the oxidation potential, sum of the two. these potentials, but our usual convention is that to write this electrode potential in terms of this reduction potential, and oxidation potential, reduction potential for this particular species have the same magnitude, only this sign is reversed. So this we can write this E copper plus 2 oblique copper and minus E zinc plus 2 oblique zinc. This is also reduction potential, this is also. So we can write this E right hand side electrode minus E left hand side electrode. And also it is proper that this is the positive electrode, this is the negative electrode. Positive electrode is having the higher potential than negative potential. So potential difference of this cell, this one is higher, this one is lower. Current will move from this to this. However, electron will flow from zinc to copper. Here this electrode acts as the source of this electron, and this electrode consumes this electron. If we connect these two by means of an external circuit, by an external circuit. So similarly E cell naught, also we can write this E copper plus 2 copper naught minus E naught and zinc plus 2 and zinc. And these two are the standard electrode potentials. So when the activity of this zinc ion is taken equal to 1. So these values we can obtain from a standard table of a physical chemistry textbook. So this value is given here, the 0.34 R value, and this one is minus 0.74 and this one 1.1 volt. This is the standard potential of this electrode. So this Nernst, whenever we apply the Nernst equation, say suppose at 25 degrees centigrade, these are at 25 degree centigrade, we get this result E shell equal to 1.1 volt minus 0.059. Here 2 electrons are involved, means 2 gram equivalent change occurs. So 2 and log activity of the zinc plus 2 and activity of the copper plus 2 and other terms, this is solid, their activity is taken 1. So as the Nernst equation not only used for this cell reaction, but it is equally valid or applicable for the case of this electrode reactions. In this case it will be similarly zinc plus 2 oblique zinc, it will be equal to zinc plus 2 zinc naught, standard value, standard electrode potential, minus 0.059 by 2 and log activity of the zinc plus 2, and this activity is taken equal to 1. So this E copper plus 2 oblique copper, and this will give you the copper plus 2 oblique copper naught and minus 0.059 by 2 into log and 1 by activity of copper plus 2, as the copper atom is having the activity equal to solid copper activity equal to 1. So this is all about the Nernst equation and expression. These are these two equations.
Yes.
So this equation also we can apply to determine the activity equilibrium constant for this cell reactions. In case of a Daniell cell, already volt equal to 0.059, and here for this Daniel cell, two Gram equivalent reactions occurs, and so it will give you this log Ka. So from this we can calculate this activity equilibrium constant, and whenever calculation is made, this Ka is equal to 1.66 into 10 to the power 37. So this value is very high. Of course, at 25 degrees centigrade. Now I shall try to explain how this single electrode potential could be determined experimentally. It is better to know. It is not possible to determine this single electrode potential by means of any instrument, as this single electrode reaction does not occur. Oxidation, reduction, both these two reactions occur simultaneously. So this, and we get, suppose E cell equal to potential of this cell. We get this right hand side electrode potential minus the left hand side electrode potential. So this one could be determined by means of a potentiometer. But this is equal to the difference of these two electrode potentials. Unless and until we know the value of one, the other could not be calculated. And this single electrode potential would not be determined by means of any instrument, as single reduction reactions or oxidation reactions cannot occur individually. So for that reason, one electrode we have chosen whose potential have been taken 0, and this one is normal hydrogen electrode, and it is written as H plus, and activity of this hydrogen ion equal to 1, and hydrogen gas passed at 1 atmosphere, and the potential, this is the standard hydrogen electrode, as both this, here the activity equal to 1, and activity of this gas is equal to the pressure in the atmosphere unit. So this is also activity equal to for this hydrogen gas is 1. So it will give you, it is called the standard hydrogen electrode. In short, we call standard hydrogen electrode, whose potential, and so the potential of this standard hydrogen electrode is taken 0 at any temperature, and this potential, this electrode is very popular, and whenever we try to determine the potential of any one electrode, another electrode must be this standard hydrogen electrode. This electrode is, sketch of this electrode will be like this one, and this is platinum. Platinum is platinized with platinum is deposited platinum black, and here it is the acid solutions of activity of hydrogen ion equal to 1 taken, and this is hydrogen gas. Hydrogen gas is passed through these solutions. It is gas, 1 atmosphere, and this is the terminals, and the potential of these terminals means E8 plus oblique H2 and standard value equal to taken 0. So if we like to determine the potential of this zinc plus 2 zinc plus 2 electrode, if we like to determine the potential of this electrode, then we shall have to set up one cell of which one electrode will be naturally a standard hydrogen electrode. So this will be equal to zinc, and suppose zinc plus 2 and down vertical line, and here is standard hydrogen electrode. Standard. This is the positive electrode, and this was negative electrode. Zinc is more electropositive than hydrogen gas, and so this E cell equal to E of this right hand side electrode minus E of this left hand side electrode, and this is equal to this E of the standard hydrogen electrode, or we can write this hydrogen H plus oblique H2, and this one is E zinc plus 2 oblique zinc. This one is taken 0. So 0 minus E zinc plus 2 oblique zinc. So the potential of this zinc ion zinc equal to minus E cell, and this one is determined by means of potentiometer, and this will give the value of this zinc ion electrode. By this way, all other potential of other electrodes are also being determined by using this standard hydrogen electrode, whose potential is 0 at any temperature. So this is all about the Nernst equation and electrode potential, its origin and determination. Thanks to you all for watching this video. In my next lectures, I shall try to categorize the type of electrodes in full details, its representation and type of the electrodes, and each electrode representation, electrode reactions, electrode potentials, and any applications of this electrode, if it could be available. All this I shall try to explain in this next lectures. Thank you all.